Oh, now it's not showing up. Techniques for integrating that we have not used before. So I think one of the big surprises is that sometimes you might use something from Algebra 2 that we have not used in a really long time, which is the technique of completing the square. So the idea of completing the square was that we would try to figure out what number we need to add right here that would take this quantity and turn it into a perfect square. And so if you remember, the method that we would do is we would take that b value, -8, divide it by 2 and get -4, and then we would take that -4 and we would square it. And so 16 is the number that we need to add to complete the square. And if we add 16 to one side, then of course we need to add 16 to the other side. So what does that leave us with? Well, on this side, that would be x minus 4, the quantity squared, x, and then you take the square root to get the 4 there. And we would need to subtract, of course, if we had a -8 there. And on the other side, we're going to have 41. So how would we solve by completing the square? We would take the square root of both sides. Don't forget that we'd have a plus or minus there. And then we would add 4, which would give us x equals 4 plus or minus the square root of 41. So we're going to use this technique today to help us to integrate. There's a few other things we need to remember. If you recall, we took some derivatives of inverse sine, inverse cosine, and inverse tangent back in Chapter 3. This is also known as arc sine, if that helps you remember. And those derivatives, which we really don't use very much, are 1 over the square root of 1 minus x squared for arc sine. Cosine was the exact same thing except it was negative. And tangent was 1 over 1 plus x squared. So those are going to be relevant to working with these problems in the future. In example 1, we're going to use the technique of completing the square in the denominator to change that integral around a little bit and make it look a little bit different. Now we don't have an equals sign here in the same way we did in the first one. But what we're going to do is we're going to think, what would we need to put here to complete the square? And so I would need to go over here and I would take 4, divide it by 2, and then I would square that and get 4. So if I wanted to complete the square, I would need to put plus 4 there. I originally had plus 5 though, which means that I need to have plus 1 more on the bottom here for this to work. X squared plus 4x plus 4 plus 1 is the same as x squared plus 4x plus 5. And why do we prefer x squared plus 4x plus 4 plus 1? Because we can take this first part here and change it into x plus 2, the quantity squared, plus 1. So why is that helpful? Well, if we do a u substitution, then we're going to see that, oh, sorry, got a little mistake there, x plus 1 and du would be dx. And so this u would become 1 over u squared plus 1 du. Now ordinarily that might be an integral that we had trouble integrating, but if you remember when we went back here, I'm having some weirdness here. I'm afraid I'm going to mess up if I try to fix that. So if you remember that when we had on the other page that the derivative of the inverse tangent was 1 over 1 plus x squared. And this fits that mold. So this is actually the inverse tangent of u plus c. And of course we would go back and fill in our inverse tangent with the u instead with x plus 2. And that is equivalent to to this integral. So in example 2, we've got something quite similar. The only difference being that instead we've got a negative in front of our x squared there. And so we're going to end up doing we're going to complete the square with that. I'm going to be happier if it's negative. If it's positive. So I'm just going to go ahead and do this. And I'm going to figure out what we need to add in here for this to work. So half of 8 is 4. 4 squared is 16. So we would want to add 16. Well, that's the same as subtracting 16 with that minus in front. And so if we wanted to have minus 15, and we currently have minus 16, we would need to add 1 here. That's going to give us, if we simplified all this out, negative x squared minus 8x minus 15. And so integrating that, that would be x plus 4, the quantity squared, plus 1, which I could rewrite as 1 minus x plus 4 squared. And if you notice, that looks kind of like our inverse sine derivative, especially if we do a substitution of u equals x plus 4. So if we do that, we're going to end up with the integral of 1 over the square root of 1 minus u squared du, forgot my dx here. And we know that that antiderivative is going to be inverse sine of u plus c, which is going to be the inverse sine of x plus 4. So the second technique that we're going to use is involving another method you might have forgotten from Algebra 2, long division. So just a little recap of how we do long division. You're going to put that x minus 3 outside and the x cubed minus 4x plus 7x minus 6 inside. And so we would check to see how many times does x go into x cubed, and that's going to be x squared. X squared times x is x cubed. X squared times negative 3 is negative 3x squared. If you remember in real long division, at this point, we would subtract. So we need to subtract this whole thing, which is going to get those guys to cancel. Negative 4 minus negative 3 is like plus. So negative 4 plus 3 would be negative 1x squared. Bring down the 7x, which is positive. Now we want to check how many times does x go into negative 1x squared. That would be negative 1x times. Again, we're subtracting that whole thing, which is going to cause these guys to cancel. And that's going to give me over here 4x. Bring down the minus 6, and we're going to get 4. Subtract the whole thing, and that will give us a remainder of 6. So we could put plus 6 over x minus 3. So why did we do that? Well, we did it because if you're in a situation where the numerator is a higher degree than your denominator, there are times when doing long division can help you to convert this integral to something that you actually know the value of. So I'm going to take a little time, and we're going to do long division with this bad boy. So we've got the 2x plus 1, (4x cubed). I'm going to put in a 0x squared because I have to have something for all my terms in long division. Okay, so let's compute this over here. So we're going to have 2x squared and we're going to end up subtracting that whole thing. which is going to give us negative 2x squared. Bring down 5x. Negative 2x into negative 2x squared goes in negative 1 times. Sorry, negative 1x times. And that'll give us negative 1x. Subtract that whole thing. 5 minus negative 1 is going to be 6x. And we're going to bring down minus 1. And that'll give us 3 here. So 3 times 2x is 6x plus 3. Subtract the whole thing. And we'll get negative 4. So that would give us plus negative 4 over 2x plus 1. How does this help? Well, if I convert this integral right here into 2x squared minus 1x plus 3 minus 4 over 2x plus 1, then it's the same thing as what we had before. Why does that help me? Because 2x squared we know how to take the antiderivative of. That's going to be 2/3 x cubed. And x we know how to take the antiderivative, 1/2 x squared. And 3 we know how to take the antiderivative, 3x. And this guy right here, we know how to take his antiderivative as well. We just need to use a u. So what would my u substitution be? U would be 2x plus 1. Du would be 2 dx. So dx would be 1/2 du. So I would keep all this. I'm going to take my 4 and I'm going to pull it in front. And that's going to give me 1 over u. Dx is 1/2 du. As I pull this guy in front, I'm going to get negative 2 integral of 1 over u du. And so I'm going to copy all this down again. And the antiderivative of 1 over u is natural log of the absolute value. And I'm going to plug in for u 2x plus 1. And I wouldn't want to forget plus c in my answer. Very similar problem in example 4. Again, my numerator has a higher degree than my denominator, so I can do long division. So I'm going to get x here. Subtract the whole thing. And so this integral I can replace with x plus 2 plus 4 over x minus 2 dx. My beginning part is quite easy to take the antiderivative of. My second part is going to take a little more work. I'm going to go ahead and pull that 4 in front. Again, I'm going to use a u substitution of x minus 2. You might be able to do this one in your head. If you didn't want to use a u, you wouldn't have to. The antiderivative of 1 over u is going to be natural log of the absolute value of u, but u, of course, is x minus 2. And we would put plus c. So it's really tempting in example 5 to think, we just need to do long division because that's what we've done in all of these problems. However, in the first 2 problems that we did, the degree of the numerator was higher than the degree of the denominator. In this case, the degree of the denominator is higher than the numerator. If we do long division, we are not going to get anywhere. So we need to look at this problem kind of carefully and think outside of the box a little bit. What would we need to do to take this antiderivative? This is actually a problem that you could have done in the last section that we did. You can just set up a u to begin with. We don't need 3x squared dx. All we need is x squared dx. So we would do 1/3 du. So that would give us 1 over u times 1/3 du. So the moral of the story is just because you see a quotient does not mean you need to do long division. Long division only works if your numerator's degree is higher than that of your denominator.